This is the next video in the chapter on chemical bonding and molecular geometry. We have talked for a long time now about molecular geometry and all of the possible shapes, but we need to revisit something we talked about way back before geometry, before Lewis structures, which was dipoles. We need to add one more point about them now that we know about three-dimensional geometry. So remember when we talked about the types of bonding, covalent and ionic, and we said there were technically two types of covalent bonding. So those two types were pure covalent, sometimes called nonpolar covalent, and polar covalent. So when we had that discussion, remember that we said that the difference was in the level of sharing. In a pure covalent bond, that bonding pair is equally shared between the two atoms. The two electrons in the bond spend an roughly equal amount of time near each of the two atoms, whereas in polar covalent, there is unequal sharing of those bonding electrons. The bonding pair spends more of its time near one atom than the other. So we gave the example of dichlorine, a molecule where both of the atoms have the same electronegativity, as an example of a pure covalent bond. And we represented where the electrons might be located by drawing a shape that shows roughly equally sized circles around each of the atoms. And when we talked about polar covalent bonds, we used something where the two atoms had very different levels of electronegativity. And we said that the more electronegative atom chlorine is more able to attract the electrons from that bond to itself. So we could represent where the electrons spend their time as spending more time next to the chlorine than next to the hydrogen. So there is unequal sharing happening in this bond, and there is equal sharing happening in this bond. I hope you also remember that we used some symbols to indicate which of these atoms was the more electronegative of the two. We labeled the more electronegative atom with this lowercase delta with a minus sign. It indicated it has a partial but not a full negative charge. And we labeled the less electronegative or more electropositive atom with a lowercase delta plus as a partial positive charge. And we drew what's called a dipole arrow pointing towards the more electronegative atom with a little plus sign at the other end. So this is what the tools that we used for small molecules. And now we're talking about slightly larger molecules, and we need to take these arrows to the next level. So when we're talking about a molecule that has more than two atoms, we need to draw one dipole arrow for every bond in that molecule to be able to appreciate where the electrons in each of those bonds are located. So one dipole arrow for every bond. So here's a simple molecule that we know, H2O, which has more than two atoms, specifically 3. So we want to look at each of the bonds and we want to draw a dipole arrow representing which end of the bond is the more electronegative end. So oxygen is more electronegative than hydrogen. It's closer to the top right corner of the table. So for this bond, we are going to draw the arrow pointing towards oxygen, and we're going to make sure that we draw the dipole arrow at the same angle as the bond, or as best as your drawing skills can handle. And for this oxygen-hydrogen bond, we're going to draw a dipole arrow also pointing towards the hydrogen. So in both cases, the arrow is pointing towards the oxygen, both the arrows are pointing towards the oxygen, but the actual direction, left or right, that they're pointing is slightly different. So the big hurrah we're going to add to our picture is we are going to add together all of the bond dipole arrows to make one giant arrow. So the sum of all the bond dipole arrows, also called bond vectors in calculus, this is called the dipole moment. Or sometimes we call it the net dipole because it's the sum of all of the small bond dipoles. These are your terms that you're going to want to know. So what we do is we think about in three-dimensional space, if we added all of these little red arrows together to get a large arrow, which direction would that large arrow point? So if we think about how this first arrow is pointing slightly to the right and the next arrow was pointing slightly to the left, that right and left pointing are going to cancel each other out, but both arrows are pointing slightly towards the top of the molecule. So our dipole moment, the sum of both of those arrows is going to point straight up. Because the left and right movements canceled each other out, only the upward pointing bits were left. Let's do another practice, just to be clear. We'll take this HCN molecule, and for each of these bonds, we want to draw a little red dipole arrow. Even though this one is a triple bond, we can still draw a dipole arrow. And let's go ahead and double check the table to make sure we're okay. Carbon and nitrogen are really close together, but nitrogen is slightly closer to the top right corner. So we'll draw a small sized dipole arrow. You can indicate that a dipole isn't very big by making the arrow a little bit smaller. And that in this hydrogen-carbon bond, the carbon is going to be more electronegative and the difference is a little bit more significant, so we'll draw the arrow being a little bit longer. So those are our little bond dipole arrows. And when we want to draw our big dipole moment arrow, we can see that there's only right pointing arrow. There is no up or down or left pointing nature to these arrows at all. So we'll simply add them together and get a slightly larger right pointing dipole moment. So as we start to add more bonds and we have more than two arrows, it starts to get a little bit trickier to add together, but this is the general idea. And so we have special names for molecules where we can draw a dipole moment like this. So if we have a molecule with a non-zero dipole moment, meaning we can draw the arrow because the black arrow exists, we call this molecule polar. Because you can think of the molecule as having two poles, a very electronegative pole and a very electropositive pole. And that's why polar covalent bond is named like this, because every polar covalent molecule that has unequal sharing has one end of the bond or one end of the molecule that has more electronegativity. And if we have a molecule with a dipole of 0, we are going to call that nonpolar, because we cannot draw a dipole moment arrow. There isn't one. We can go back to these pictures that we've already drawn and we can label them as polar or nonpolar. So for example, for this H2O molecule, we can see that there are bond dipoles and we can draw a dipole moment arrow. So this molecule is going to be polar. For our HCN, we can draw bond dipoles, check, and we can draw a dipole moment arrow. So this molecule is going to be polar. For our HCl that we drew up here, we can only have to draw one dipole arrow because there's only one bond in the entire molecule. And so there's going to be polar in this one as well. Up here, we cannot draw a dipole arrow for this bond because the two atoms are equally electronegative. So this molecule is going to be nonpolar. Now, I want to give you one more example of a situation where it's a little bit more difficult to figure out whether something is polar or not. And that is in a molecule like methane that has a particularly high level of symmetry. As you continue in your chemistry career, you'll see that very, very high symmetry molecules are particularly interesting to scientists. So if we draw in a tiny red bond dipole arrow for each of these bonds, we would draw it pointing from the hydrogen towards the carbon because carbon is more electronegative. So we have a small arrow pointing this way towards the carbon, a small arrow pointing this way towards the carbon, a small arrow pointing this way towards the carbon, and a small arrow pointing this way towards the carbon. So, do we have bond dipoles? Yes, we do. There is more than one type of atom in this molecule, so we can draw bond dipoles. The question is, what will the the dipole moment look like in this picture? It's a little difficult to figure out because we're adding together 4 arrows, and you might need your 3-dimensional molecule to help you answer this question. But if you think about a molecule of this particular structure, there is a downward pointing arrow on this bond, and each of these other 3 bonds has a slight upward facing component that cancels each other out. We have a slight left facing arrow on this side, a slight right facing arrow on this side, and those cancel each other out. So although it's difficult to note from a 2-dimensional picture, there is actually a dipole moment of 0 in this picture. So we cannot draw a dipole moment arrow, even though we have a bond dipole for each of these bonds. The overall molecule has a dipole moment of 0. And that is because of its extra special high symmetry. If we were to replace even one of these hydrogens with something else that wasn't a hydrogen, the left, right, and up, down components of these vectors would not fully cancel each other out. But because of the nature of a tetrahedral shape and the fact that all of those terminal atoms are the same, the bond dipoles cancel each other out. So not every molecule with bond dipoles is polar. So this molecule is going to be nonpolar because all of those tiny red arrows cancel each other out. And the reason we care about polar molecules is that on the macroscopic scale, they are actually really interesting. So let me give you a preview of why we think this is worth caring about. There are 2 particularly interesting features about polar molecules. The first is that when you take these molecules and you put them in an electric field, they all slowly turn and orient themselves in the same direction every time. Specifically, if you have a negatively charged plate and a positively charged plate, so you have an electric field created between them, and you take a water molecule, which we know has a slightly negative end by the oxygen and a slightly positive end by the hydrogen, the slightly negative end will point towards the positive end of the electric field, and the slightly positive end will point towards the negative end of the electric field. So we have our slight negative here by the positive end, and we have our slight positive here by the negative end. So that's the first cool thing that polar molecules can do. The other cool thing they can do is that they dissolve other polar things. So polar molecules dissolve in other polar solvents. For example, oil dissolves in water because both of those are polar. This is how we make salad dressing. We can dissolve some things in other things because those polar nature of the molecules are very similar. So we have now learned everything that we need to know about Lewis structures and geometry and its effect on the dipole. So we now need to cross off geometry and shape from our Adam's first approach. We are almost done learning everything we need to know about molecules. We learned about bonding types, nomenclature, Lewis structures, and geometry and shape. So we are ready to move on to the next chapter on orbital energies and shapes.